Our last speaker of this morning is Jonathan Heckman, and he's going to tell us about the generalized symmetries of non-supersymmetric orbifolds.
Okay, so first of all, thanks very much to the organizers for putting this great meeting together and also for giving the opportunity to talk about some stuff I've been thinking about recently. I'm going to continue in the theme of talking about aspects of symmetries, but I'm going to try to apply some of the lessons that have been learned in certain supersymmetric systems now in the context of certain non-supersymmetric backgrounds. So this is based on a paper that appeared rather recently with two students at Penn, Noah Brigger and Vivek Chakrabarty, as well as Max Hubner, who's there, the postdoc at Penn, as well as some other work involving various permutations of people who are in the audience. And I'm sorry if I omitted anybody in the references on the slides that follow. It was not intentional, unless it was. But it was not intentional, so sorry about that if I omitted something by accident. Okay, so this has already been kind of discussed a bit, so I'll try to be brief. The key idea in the context of generalized symmetries in quantum field theory, now about a decade old, is to kind of revisualize or reformulate what we mean by a symmetry in terms of a more topological object. So something that kind of links with, say, a extended operator of interest. So here I've indicated, for example, a symmetry operator n sub q, supported on a q-dimensional manifold, and O sub p, some defect or some other operator supported on a p-dimensional subspace. And the action of the symmetry operator on the O sub p, the defect, is obtained by just shrinking it. And the key idea is that this is topological. It doesn't really matter what the shape of this dash thing is, so long as linking or intersection is maintained. And this has been extended in many very interesting ways. Higher p-form symmetries is a simple example. Higher group symmetries, where not just one p-form symmetry, but possibly two, are acting on the same object, possibly entwining with one another. And even bigger generalizations involving, say, non-invertible, fusion, or categorical symmetries. Now, where does string theory enter the game from this point of view? Well, it's kind of, if you're interested in symmetries from this point of view, it's kind of indispensable to use strings. If we're talking about, for example, higher dimensional conformal fixed points. This is basically the way we know how to engineer these theories in the first place. So if one is interested in these symmetries in the first place, probably the geometry of the string compactification or string background is a very helpful way to proceed. More generally, if you take one of these strongly coupled fixed points in higher dimensions and then start compactifying, you get to a large set of non-Lagrangian field theories. And again, one can use this geometric starting point to then start studying aspects of these symmetries. And lastly, I'll mention it. I'm not going to talk about it too much. I'm not going to talk about it today. But in these configurations where we have some local model that's engineering the quantum field theory of interest, there's then a built-in mechanism for them to ask what happens to these symmetries when we start switching on the effects of gravity. So we can take this local model and try to put it inside of a compact model and then track what happens to the defects, the symmetry operators, and so on. Okay, now the thing I want to emphasize is that most of the lessons, as they've been developed so far, have been applied in the context of supersymmetric systems. This is for a very good reason. This is basically the arena in which we know how to build the field theories of interest and engineer them from a string background. But it's worth asking, these things that we're talking about, these symmetry considerations, are rather topological in nature. So one might ask, do we really need supersymmetry to make some of the statements or some of the structures that are, investigate some of the structures we've been seeing in these supersymmetric settings? So what about non-supersymmetric backgrounds? So first of all, supersymmetry is broken, so you're going to have to deal with that eventually. And a very natural question is, what are some robust non-supersymmetric tools to develop? So something that is topological is complementary to those kinds of investigations. Okay. Yes. So here is the typical supersymmetric setup for engineering a kind of background of interest. So here is going to be where my quantum field theory is going to live. This is supposed to indicate, say, Minkowski space in d-dimensional spacetime dimensions. And what we're imagining is some kind of localized singularity or localized configuration to engineer the field theory of interest. So we're imagining that there's, say, some branes or open strings that are kind of trapped into the singularity, and then the closed strings are decoupled from the system. And I'll typically just focus on the case of a conical geometry, so there'll be a radial coordinate extending out, and then there'll be what I'll refer to as the conformal boundary, or just the boundary of this conical geometry. Okay, so how do you make a defect in this setting? You take a brane, and you let it extend from the tip of the cone out to infinity, and whatever directions were not used in the extra dimensional piece, in the conical piece, this will give you the dimension of the defect inside of the field theory sector of interest. How about a symmetry operator? Okay, so if we were interested in making a symmetry operator which acts upon that thing, we want it to topologically link here. And the case I've denoted here is actually what's been worked out from various points of view, both from geometric engineering, holography. Sorry, I forgot to put the references here. But the idea is that they link both in the space-time as well as, if you like, off on the boundary topology. This is for the case of discrete symmetries. There's an analogous story that can be told in the case of continuous symmetries. Okay, I'm going to kind of focus on the crudest version of trying to figure out some aspects of higher form symmetries, something referred to as the defect group. And if you pick this and then you pick an appropriate subset of the things produced by the defect group, you get the corresponding p-form symmetries. I'll leave that part implicit, but I'll indicate how it will go in various cases. So what is the defect group? Well, basically what we do is we look for all the possible branes, and we look for the ones that can possibly be screened out by dynamical states. These dynamical states come from branes or other objects wrapped on compact cycles, namely hk+1 cycles inside of X. And then the defect itself is wrapping this non-compact relative cycle, which extends from the tip of the cone out to the boundary. The quotient are the things basically that cannot be screened out. And so we just take a sum over all the possible choices of branes and cycles to figure out this candidate, the defect group. And this is a story that's now been developed over several years. And so I'm going to basically be computing in the rest of the talk things related to the defect group. So in other words, once you have this defect group, you can get from this, if you take a particular subset of the defect group, the corresponding higher form symmetries. Okay, so what's going to happen in the non-supersymmetric case? Does this still work? So this is the picture I want to draw. What will happen in this kind of setting? So I'm going to be looking again at string backgrounds of the form of some, if you like, a 4D spacetime over here, and some singularity over here. But I'm going to relax the condition that I have supersymmetry now. Okay, so what's the main complication? So this is well known that there's many complications from doing this. The one that we're going to be focusing on today is the one associated with tachyonic instabilities of various kinds. Now, it has been found that there are cases where you can get a tachyon which is kind of localized, say, in a closed string twisted sector. And so in that sense, it's still doing something. It's still generating an instability, but at some level, it's under more control than if it had been, say, a bulk tachyon, just destroying the entire spacetime right off the bat. So what I'm going to do is, number one, engineer the tip of the cone, the local system of interest. This is not going to be sequestered from the tachyon in any sense. How could it be? It's right where all the action is. The defects will also be introduced by having an object, a brane, which extends from the tip of the cone out to infinity. These are not really sequestered either because the defect is touching the cone, but it's a big, heavy object, and so there's more control over it. It also extends out to infinity, where the tachyon has not leaked out yet. And then finally, and this is, I think, the crucial point, the symmetry operators, which, if you remember, were at infinity. They were at the boundary of the conical geometry. They were very far away from where the tachyon was initially localized. So there's a hope that we could talk about these symmetry operators as the tachyon starts to roll down and generate an instability of some kind. So that's what we're going to be tracking as we go. Okay, so my focus for today is going to be on this system, type 2A, on basically 4D Minkowski space, and I'm going to take a particular non-supersymmetric quotient. I'll refer to this as the pure geometry setting. If this had been a non-compact Calabi-Yau threefold, and if it had had a collapsing 4 cycle, we would have been generating a 4D n=2 SCFT. As it stands, we're not going to be generating that. There'll be no supersymmetry preserved at all. I'll also briefly mention there's a same geometry but different physical setup where we take type 2B on the same background but instead put a bunch of D3 branes probing this singularity. In that case, if this had been Calabi-Yau threefold, you would have gotten a 4D n=1 SCFT. In the non-Calabi-Yau case, this produces a non-supersymmetric 4D quiver gauge theory, which has also was heavily investigated in the past. Okay. So non-supersymmetric orbifolds, here's just a sampling of the references, both for brane probes of these spaces, closed string tachyons in these spaces. And what I'm going to be doing is asking, can I play the game of computing generalized symmetries in this kind of background? Okay, so I'm going to pick a finite subgroup of SU4, and I'm going to pick it in such a way that the holomorphic 3 form of the original R6 or C3 cannot be retained. So in other words, I've decided to pick a particular finite subgroup so that there is no killing spinner available to me. That will ensure that I've broken supersymmetry. Okay, what are the possible singularities we can encounter? Well, we have one at the tip of the cone. But there could be other things depending on what the group action in consideration is. So once I tell you the finite subgroup, that's not enough. I also have to tell you how does this group act on the geometry itself. So I've just indicated some of the singularities. There's the one I'll call a codimension 6. This is kind of the tip of the cone. We'll always have that. But then depending on the group action, there could be other things. For example, there could be a codimension 4 singularity localized on R4 mod gamma. In the case where this is a supersymmetric quotient, this would have made what we would call a flavor symmetry. It would engineer, say, an ADE type singularity, which would be interpreted as a flavor symmetry in the 4D system. More generally, however, it need not be the case. And finally, codimension 2, these are pretty big ones. These also will always be breaking supersymmetry. Why? Because there's no group action I can pick for you such that a holomorphic one form is going to remain invariant. So these are in some sense the most violent of the singularities. You'll notice also that these things are non-supersymmetric. They have tachyons, and they're already sticking out at the boundary. And because they're sticking out at the boundary, there is no sequestering that occurs in that setting. So the case where we expect to have maximal control is where we just have this localized singularity. Maybe we have some control if we have a codimension 4. And if we're lucky, we can still say some interesting things about the codimension 2 case. OK, so what kind of tachyons? I already said this, but I'll say it again. We'll always have a tachyon here, and we might have more tachyons depending on the dimension of interest. Let me first begin with the simplest case, where we expect the game to kind of work pretty well. What happens here? So as has been studied in the past, what happens is that there's a tachyon, a closed string sector in one of the twisted sectors, tachyons, and it starts eating up the original singularity. And I want to emphasize that by the time the tachyon is resolved out, usually you're left with a supersymmetric singularity by the time you're done. So this could either be just flat space, R6, but it could also be a supersymmetric Orbifold of the form C3 mod gamma with gamma, a finite subgroup of SU3. So the thing expands out. What's happening? Well, we can play the game of putting the defects and the symmetry operators in the system at early times before the tachyon is fully condensed, and at late times after it has started to condense and has started eating up both the dynamical states and the defects of interest. So what we're going to do is we're going to try and calculate the defect group, the spectrum of branes and quotienting screening, here as well as here. OK, let's begin over here. This case, by the way, will be basically just a small parenthetical remark, because I'll just redefine what I mean by the boundary of the geometry. I'll just slice it off here and then scale it out again, and I'll have a new notion of what I meant by off at infinity. So this will be actually enough to kind of get the main pieces of the story going. OK, there's actually two ways, well, three, that I know of for calculating these kinds of p-form symmetries. One is to directly compute the corresponding singular homology of the boundary lens space, this generalized lens space, this S5 mod gamma. There's another complementary approach which yields the exact same answer, at least in the supersymmetric settings, where we consider probe states, probe branes of the singularity, and then write down an associated quiver gauge theory. From that quiver gauge theory, one can extract the corresponding Dirac pairing between electric and magnetic states, and that turns out to be good enough to calculate, for example, the higher form symmetries, the higher form electric and magnetic one-form symmetries. So these are two complementary approaches that have been extensively checked in the supersymmetric setting to yield the same result. Let's see what happens in our case. The third one that I'm not going to mention is, or not talk too much about, is where you explicitly blow up the geometry and then start calculating all the different intersections of the blown up cycles. Computationally, that is really challenging when you get to more complicated singularities, so I'm not going to talk about that one. I'm not even sure I know how the method completely works in the non-supersymmetric case. OK, so let's begin over here in the geometric case. What do you get? Well, we can calculate. So there's a long exact sequence in relative homology, which in these cases actually collapses to a short exact sequence. And the quotient of the defect screened by dynamical objects just becomes the H1 of the boundary space. In the case where this thing is an isolated singularity, namely it's freely acting on the gamma, then you'll just get, say, Z mod n, or whatever that gamma is. In the more general case where there is some fixed locus, there's a theorem that was worked out by Armstrong which calculated pi1 of the space. H1 is the abelianization of pi1, and you basically just have to quotient out by whatever the subgroup is that left something fixed. So this is a known story that has been nicely developed. And so, for example, in the simplest case where it's a freely acting Zn, you always get a Zn, say, one-form symmetry. How about the other approach where we work in terms of a quiver? Well, here we want to just look at what probe state C. Now, as was observed, I don't know if you can see it, but there was a nice paper here which observed that if you know something about the Dirac pairing, then the torsion of the co-kernel of that Dirac pairing directly extracts for you the electric and magnetic one-form symmetries for the system. And so I've tried to indicate this here by just drawing two heavy world lines and asking what happens if we do monodromy of one around the other one. How does it work in our setting? Well, I need to somehow figure out what the Dirac pairing is. Where is that? So it turns out that that thing is captured by data directly encoded in the associated non-supersymmetric quiver quantum mechanics of the probe states. So for example, if you know something about the D0 brane at this singularity, this is an algorithm that's been worked out in the past, it turns out that there are two adjacency matrices to talk about, one for the fermionic states. These are open strings that stretch between the different fractional branes, if you like, under the group action of the orbifold group action. And they have the fermionic states as well as the bosonic states. It turns out that the one that is relevant for constructing the Dirac pairing is directly tied to the fermionic degrees of freedom. In particular, if you take this adjacency matrix and anti-symmetrize it, it turns into the Dirac pairing. And so the defect group just becomes the torsion of the co-kernel of that thing here. Here I've drawn what the quivers look like in a specific case. This is R6 mod Z5, and the group action I'm indicating here is on the spinor representation of spin 6, or the fundamental of SU4. So that's why I've listed 4 weights here. All 4 weights have to sum up to 0. But if you just look in terms of what it does on the holomorphic, the candidate holomorphic 3 form, it would not have been invariant. And so the quiver for this particular case was studied in the past, as well as the associated tachyon condensation picture. Okay, now we can calculate in both these cases, and lo and behold, they exactly match. So in these cases, so we check this in a ton of examples, and one can argue on general grounds that one expects it to kind of work in this way. The defect group predicted by geometry based on singular homology, and that based on this quiver quantum mechanics approach, where we just directly look at the Dirac pairing and start extracting the torsion of the co-kernel of the Dirac pairing, they exactly produce the same answer. What about non-isolated singularities? So there I said we have to tread with more caution because the tachyon is now possibly out at infinity, and the geometry itself may be messed up. Well, there are 2 cases one could entertain, a codimension 4 singularity or a codimension 2. It's possible, and in fact, in all the cases we explicitly found, or we could explicitly write down answers for, it turned out that the R4 mod gamma prime induced from the original group action for the R6 mod gamma turned out to already produce a supersymmetric R4 mod gamma prime. So there's no extra tachyons in those cases. When you have codimension 2, no such luck is available, and you will definitely have a tachyon out here. So in the case where there is no tachyon at the boundary, so the tachyons are still sequestered at the tip of the cone, turns out that, again, you get an exact match between the geometric answer for the defect group and the quiver answer. So that's, again, a very nice match. Having this extra thing floating around causes no extra problems. What if there's a tachyon at the boundary? Now, something does change. You get 2 answers. You can recompute these 2 things. This is, again, a straightforward task. What you find is that actually now the geometric answer and the quiver answer do not agree. So there is a mismatch. That's, if you like to be, well, if it had matched, of course, I would have said, that's wonderful. It shows how powerful the geometry was. But if it doesn't match, you have an out. You can say, well, I didn't expect necessarily that it would match because there were tachyons off at the boundary. Who knows? Maybe something has gone badly awry. But it goes badly awry in a very controlled way, so it's actually not as bad as you might have thought. You get the geometric answer plus some subleading correction terms. And what these subleading correction terms appear to indicate is that as the tachyon at the boundary pulses out and starts partitioning up the boundary 5 sphere mod gamma, there's other places where you have fixed point loci. So there's an analogous statement about gamma mod gamma fix. I've written it as a gamma mod h to fit with the notation of our paper. You get a direct sum over these extra pieces. And these are well-known things. So if you, from the group action on the boundary 5 sphere. So the quiver answer actually splits into the naive geometric answer plus some subleading corrections as associated with partitioning up this S5 mod gamma into finer pieces. So in fact, at this point, it's really an empirical formula. We checked it in a bunch of involved and complicated examples. But the general picture seems to be that the tachyon is just partitioning things up and allowing you to get these more general contributions to the one-form electric and magnetic symmetries. OK. I'll probably wrap up a little early since I think people want to. I don't know, how much time do I have? 5? OK, I'll try to wrap up a little bit early. So let me now try to connect this. Symmetry TFT, so symmetry topological field theory, is something that was already kind of mentioned in a few different talks. I just want to mention how what we've said here fits with that picture. So it's not quite a symmetry TFT, but it's pretty close. So here, just to remind you, OK, so I didn't list all the papers because there's, it would just fill the entire page and then several more. So I've just listed a few that are relevant for what I'm going to talk about. The basic idea is that the original system of interest is kind of viewed as an edge mode or something, and then you extend by one dimension into some gap system. So you view the original quantum field theory degrees of freedom as really some relative degrees of freedom trapped on this edge, and then the global structure of the global form of the symmetries, the defects, and so on are encoded in a choice of topological boundary conditions at the other side of this gapped bulk. And so what I've drawn here is this red defect. It gets extended by one dimension, and then the topological operator, which links here. Note that if I push this topological operator directly into the boundary, it maintains the linking. So this thing lost a dimension, but this thing maintained its dimension. So linking is maintained as I push it into the boundary. So this is a very useful device for, first of all, capturing, say, the global structures, as well as formalizing what you mean by, say, the partition function of a field theory in the first place. It's basically just an inner product between the physical state and the topological state in this corresponding gap system. That encodes what the what the partition function is. OK, how does this work in the case we're talking about? Well, we're going to start at early times. Time is running up inside of the red slice. So time is inside of the field theory direction. So in this case, there's a jump that occurs. We can calculate the defect here. And then it's not quite a sharply localized thing, but in some idealized limit, we can squeeze it down. There's some non-topological junction or interface, and then it jumps to a different piece over here. So there's a TFT up here in this region and a TFT down here in this region. More precisely, they just look like this. It's a collection of two forms. The two forms are associated with the background values of, say, the corresponding one-form symmetries. This Kij is the big K is what we get at early times. We can calculate that again directly from either singular homology or from the quiver method. And likewise, we can do it at late times. And then everything here is basically just a set of boundary conditions associated with dumping these things inside of continuous symmetries and appropriate boundary conditions to match the big B's and the little b's across this wall. So there can be very violent jumps in the values of big K versus little k. OK, so here's an example. If you take that Z mod 5, it has a single divisor in it. It's an O minus 5 over P2. The P2 starts expanding out, and you're left with just an R6 by the time you're done. So it's kind of the empty theory. There's more complicated resolutions that also occur, but this is just one of them. OK, now I'll briefly mention what happens on the 2B side. You can again do the exact same thing. This picture is really motivated by what happens if you look at, say, D3 branes. As you zoom in near the neighborhood of the tachyon pulse is expanding out. One can show that this thing looks like basically a transition from high energy scales, down to low energy scales. So this is the answer you get. And this fits very naturally. So now it's actually radially moving out. So this direction here is interpreted, roughly speaking, as an energy. And so we have 4D Lorentz maintained in this case. This fits very well with the picture of symmetry breaking that was kind of proposed in many of the earlier papers. It fits very well with that general line of investigation. OK. Other structures that I didn't really talk about too much, but are definitely there. So in the supersymmetric setting, other things that have been observed to occur are things like two-group structures. They've already been mentioned a couple times. Empirically, these things always happen when you have a non-split short exact sequence like this involving, say, the abelianization of gamma and these other pieces here. Same thing happens here. We can observe that there's two groups that are present initially, either initially present in the singularity, or ones that actually emerge as a result of tachyon condensation occurring, and then it kind of sweeps out and an emergent two-group occurs at either late times or in the infrared. Similarly, I didn't really mention it too much, but another thing you can do is put in topological duality defects by wrapping 7 branes of constant axiodilaton on the boundary 5-sphere mod gamma. In the supersymmetric setting, it's been observed that this is how you implement those duality defects. Same story works again in this non-supersymmetric setting. Why can I do that? Because at large n, for example, tau doesn't run. So it's actually quasi-marginal. So we can still talk about what happens as we put this 7 brane in. Well, generally, it's not really a duality defect. It's a duality interface, but I'm not going to split hairs on that right now. OK, I think I'll sum her up and tell you about possible future directions. There's many, I think, but I'll just mention a couple. So what is the main punchline I want to mention here? I told you about symmetries via branes at infinity. And this general framework for how we get generalized symmetries from these kinds of top-down constructions does not really require supersymmetry. In particular, the fact that things are localized, or we're talking about these symmetries being associated with things off at infinity, sequestered from where the kind of violent stuff is happening with the tachyons, provides a very good control over what is happening with those symmetries. Even when they're off at infinity, we saw empirical answers for how you could generalize the answer. We also saw the quiver method, which didn't really care at all whether they were sequestered at all. Okay, I think there's a couple of very natural directions to consider. One is considering more general non-supersymmetric backgrounds. I applied it in the case of just R6 mod gamma, but it would be very interesting to consider things that don't necessarily come from such orbifold backgrounds. Surely we can find others and study the non-supersymmetric, the generalized symmetries in such settings as well. And more generally, one of the challenges is finding healthy compactifications that are non-supersymmetric. Perhaps these kinds of symmetries constraints can provide constraints on what happens with, say, the late time dynamics of these kinds of non-supersymmetric backgrounds. When people try to write these things down in many settings, there's inevitably a point where you say, well, I don't know what's happening. The instability grew too much. I give up. But with these kinds of symmetries, it's potentially possible to say a bit more about those things. So I think that's a potentially very fruitful place to look also. I'll stop there. Thanks.